Hi everyone, today we are going to talk about exponential functions. A lot of this stuff should already be familiar to you, stuff that you've done in algebra, algebra 2. So some of it should be very familiar to you, some of it will be a little bit new. So let's just talk first of all about an exponential function, what it is, the characteristics of it, etc. An exponential function is any function written in the form y equals b to the x, and that's what we consider an exponential function. Now there's a couple of things. B is our base, and that identifies what kind of exponential function we have. We could either have exponential growth or we can have exponential decay. In order to have exponential growth, that b value is going to be greater than 1. Exponential decay would have a b value between 0 and 1. So those are the differences between those two. The graphs for growth and decay are very similar. Domain and range is the same. They just have a little bit different look to them. For exponential growth, our function, if these are our axes, our function would have this general shape. First of all, our function will go through the point 0, 1, because when you plug in 0 for x, you would get y is equal to 1, because anything to the 0 power is 1. So it doesn't matter what the base is. The base could be 2, the base could be 27. Anything to the 0 power is 1. So we know we're always going to go through that point. Oops, and what happens is our graph goes through that point and then increases exponentially. And so let's talk about the domain and the range of that graph. Our domain, right, I can plug anything I want in for x. So my domain is all real numbers. Oops. But my range, right, my graph here can never be negative, right? Because it doesn't matter what value I put in for x, if b is positive, then I'm always going to end up with a positive number. And so my graph is going to go from 0 to infinity. Also, it can never actually equal 0, because any number when you raise it to some power will never give you 0. Okay, so that is the growth function. The decay function is very similar. It just has a slightly different look to it. If these are my axes, when you graph the decay function, you're still going through that point 0, 1, but your graph ends up having this shape to it. Your domain and your range are the same as with the growth. So your domain goes from negative infinity to positive infinity, and your range is from 0 to positive infinity, not including 0. Okay, so those are the basic properties behind exponential growth and decay. Obviously there's more to it, but that's all the basics. This is stuff you should already be familiar with. Excuse me. Let's talk a little bit about transformations of exponential functions. If we're starting with the function y is equal to b to the x, right, there's lots of different transformations that we can do. We can shift left, right, up, or down. We can flip it over the x-axis. We can stretch it out vertically or shrink it vertically, and do the same horizontally. And this information is all in your book, but let's talk about vertical translations. Just like with any other function, when you shift it vertically, that's just tacking a number on the end. I'm going to write this over here. It's just tacking a number on the end. So for example, you have y equals b to the x plus c. So if you have plus 5, then it shifts that whole graph up 5 units. If you have minus 2, then it shifts the entire graph down 2 units. So that one's really straightforward. Let's talk about horizontal shift. This one, if you see your graph, or excuse me, if you see your function have the form y is equal to b to the x plus c. That tells you it's a horizontal shift, and you're going the opposite direction of that sign. So if it's plus, then you're moving to the left. If it's x minus c, then you're moving to the right. So plus means left, and a minus means you're shifting right. Okay, so those are also, that's pretty straightforward as well. If we are reflecting across the x-axis, when we do reflections, when we reflect across the x-axis, we're actually negating the y-coordinate. So reflecting, I'm abbreviating here, reflecting across the x-axis is the same as negating y. So you'd have negative y equals b to the x. However, we're never going to write it like this. So if I divided both sides by -1, I would end up with y equals negative b to the x. So that's where that comes from. If you see a negative in front, that means you're reflecting over the x-axis. You're just flipping that graph upside down. Okay, if we're reflecting in the y-axis, that means we're actually negating our x value. And so when we negate our x value, we end up with b to the negative x. And if you see that, then that tells you you're reflecting over the y-axis. Okay, and then the vertical stretch and the vertical stretch or shrink. If you have a function, it could be y, it could be f of x, with some constant in front of b of x, that tells you you have a stretch or a shrink. So if c is greater than 1, you're stretching. And if c is less than 1, you're shrinking. And with horizontal stretch or shrink, the equation is going to look a little bit different. It's going to be b to the cx, and actually it's going to be the flip-flop of this. So if c is greater than 1, it's a shrink, and if c is less than 1, it's a stretch. And when I say less than 1, I mean between 0 and 1. Let me write that down, between 0 and 1. So those are all of the different translations you can have when you're dealing with exponential functions. So for example, if I gave you the graph, or if I gave you the equation y is equal to 2 to the x plus 3 minus 1, that tells you, well, I'm shifting to the left 3 and then down 1. So if your original graph went through this point 0, 1, so that would be your original graph. After your translation, you'd say, okay, well, my graph is shifting down 1 and it's moving to the left 3. And so now my graph is doing something like this. Okay, so that's the idea behind that. Very basic terms, but that's what's going on there with those different translations that you have. That's all stuff that you've done before, but I just wanted to sort of reiterate that with you. The more interesting part of exponential functions is when we start talking about the natural base. We talk about e. Something that you've probably seen on your calculator, something that you've heard of, you never really knew where it came from. Here's the idea. If I have this expression 1 plus 1 over n to the n, and I were to put that into my calculator, right? That is an exponential function, right? Because I'm raising to some variable or some power there. So it is an exponential function. But the idea is this. as n gets larger and larger and larger, getting closer and closer to infinity, there's a certain point that this is going to reach. This is not going to go to infinity. Everybody thinks, oh, well, because of that n going to infinity, that this is going to actually go to infinity, which it doesn't. It actually approaches this decimal, and it gets closer and closer to this decimal, 2.71828 something. It goes on and on and on. And so that number is considered the natural base. Okay, and that's what E is. It's irrational. It's something that we use a lot in banking, actually, when you talk about interest and things like that. We're going to get to that in a second. But that's where it comes from. That's a really, really, really abbreviated explanation of where it comes from. But it is an irrational number. We usually approximate it at about 2.7. But if you ever see it, that's what it actually is. Okay, so like I said, that is in your calculator. You can see that in your calculator. But why I brought that up is because I first want to talk about compound interest. And if you're not familiar with compound interest, it's actually really kind of interesting how it works. And you've probably heard this example before. If you go to the bank and you say, I have $100, we'll keep our example very basic, right? If I have $100, and the bank offers you a yearly interest rate of 5%. Right? So they offer you 5% interest. Now, that means a yearly interest rate. That means at the end of year 1, you would actually have $105. That's just straight interest. Okay. Now, if it's not compounded, if it's just simple interest, at the end of the second year, you would again earn 5%, but you would only earn 5% on that principal amount that you deposited. So you'd earn another $5. So at the end of year 2, you would have a total of $110. Okay, etc., etc. And each year, if you didn't input any more money into that bank account, if you didn't deposit any more money into that bank account, you'd continue to earn 5% interest on that $100 for as long as you had it in there. Okay, so it would grow by $5 every single year. That's simple interest. Compound interest is every year you are earning interest on the money that you have in the bank, including the interest you already earned. So at year 1, you'd have $105. But at year 2, with compound interest, at year 2, you're taking 5% of now $105 instead of $100. And that would give you, hold on, I'm doing it on my calculator. That would give you $5.25 that you earned. Add that to the $105 you already have. So that gives you $110.25. Clearly not a lot more money than what you had if you did simple interest, but think of the amount of money that you would be putting in the bank, or a large corporation would be putting in a bank, right? 25 cents isn't a lot in this scenario, but the larger the deposit is, the larger the interest is, and it grows a lot faster. In the next video, I'm going to show you how this all kind of ties together.